Hello, welcome to part 2, looking at capacitors and current sources. This is the first one in which we're going to try and put a bit of maths into the analysis of what's happening, and it's probably by far the easiest case to consider. So let's just describe the problem. This one. We have a capacitor here, and we have a current source here, and we are going to connect them together with a switch. What happens just after we close the switch? Well, what we know about a capacitor is that the current flowing onto one of the plates of a capacitor is the value of the capacitor times the rate of change of the voltage across the capacitor. Here we'll assume that this current source here is constant after the switch is closed. That's the simplest case. In that case, we can call it I0. The constant value of the current equals C d dV dt. And therefore, d dV dt equals I0 over C. I can integrate this up, and that will tell me that the voltage across the capacitor is the integral of I0 over C dt. The voltage across the capacitor starts at 0, at time 0, and will just carry on to whatever time it is when I'm interested in it, or maybe call that time capital T. So delta V equals I0 T over C. That suggests that the voltage across the capacitor is linearly related to time. So if I were to plot them, I would get something like this. Always label your graphs with units. At time t equals 0, when my switch is closed, I would expect the gradient dV dt to be constant, and it would be increasing at this rate, so I would get a graph like that. Is that what happens? Well, we can see if the simulator agrees. Yep, it does. At time t equals 0, the voltage on both of these voltmeters starts increasing and heading up. And in theory, heads up without limit. That, of course, is only true in the ideal world of simulators. In the real world, the capacitors would have some maximum working voltage, and once you got to that maximum voltage, the capacitor would probably blow up. Capacitors can actually blow up quite spectacularly if you put too much voltage across them. Don't try this at home. We can extend the idea a little bit. What happens if this current source here isn't a constant current source, but it's a sinusoidally varying current source? It's maybe something that we could describe with the equation. The current is I0 times sine of omega t. So the current is oscillating up and down. Maximum value I0. Minimum value minus I0. Now what happens? Well, the voltage across the capacitor, again, would obey the equation. The rate of change of that voltage across the capacitor with time is equal to the current, which is now I0 sine omega t divided by the capacitance C. Do an integration on that, and now we have dV equals I0 over C times the integral of sine omega t dt from 0 to whatever value we're interested in. Well, the integral of sine is minus a cosine. So this would give us this. And I've missed the I0 from the top. That. We would expect that the voltage across the capacitor would also be oscillating, but with a dependency of time characteristic of minus a cosine. If we were to try and plot this, then if the current was behaving like a sine wave and doing this kind of thing, starting at 0 when time is 0, then we would expect the voltage to be behaving like a minus cosine. Now, cosine starts at 1 and starts oscillating from there, so a minus cosine would start at -1, so this would be starting down here at minus I0 over omega c, and it would be oscillating up like this. And you'd get these two sinusoidal oscillations 90 degrees out of phase. This one is the current flowing onto the capacitor, and this one is the voltage across the capacitor. You'll see that the current flowing onto the capacitor, oops, not really I0, just I, the current flowing onto the capacitor is 90 degrees ahead of the voltage. It reaches its peak 90 degrees, 1/4 of a cycle before the voltage across the capacitor hits its peak. We can just check I've got that one right in the simulator as well. Here I've added in an ammeter into the circuit as well, so that we can see the current as well as the voltage across the capacitor. And just as the maths predicted, we can see that the current here, that's the green waveform, is 90 degrees ahead of the voltage across the capacitor. That's the purple waveform here, the voltmeter. That's all for this one. Next time we're going to have a look at a slightly harder bit of maths, but a very important bit of maths. What happens when you discharge a capacitor through a resistor?